You think the speed of light is just a number. 299,792,458 meters per second. Fast. Really fast. The fastest thing we know. Fine. But why is it the limit? Why can't you go faster? What stops you? Most people have never really thought about this. They just accept it. Einstein said so. Speed of light is the cosmic speed limit. That's just how it is. But that's not an answer. That's just repeating words. When you really ask why nothing can go faster than light, when you dig into what's actually stopping you, you discover something so strange, so fundamentally different from everyday experience, that it changes everything you think you know about space and time. The speed of light isn't just a speed. It's not just the fastest thing. It's the structure of the universe itself. It's woven into the fabric of space and time in a way that makes going faster literally meaningless. Let me show you what I mean. Let's start with something simple, something everyone knows. Things fall. Drop something, it falls down. 16 feet in the first second, to be precise. That's what Galileo measured. Drop a ball, drop a rock, drop anything. In 1 second, it falls 16 feet. Now the moon. The moon is going around the Earth. It's not falling down. It's staying up there, orbiting, going in a circle. But wait, is it falling? Think about it. If the moon were just sitting there in space, not moving, what would happen? It would fall toward the Earth. Gravity would pull it in. But the moon is moving. It's moving sideways, tangent to its orbit. And because it's moving sideways while gravity pulls it down, it keeps missing the Earth. It falls toward the Earth, but keeps missing. That's what an orbit is. Continuous falling while moving sideways fast enough to keep missing. Now here's where Newton had his brilliant insight. The moon is 240,000 miles from the center of the Earth. We're standing on the surface, 4,000 miles from the center. So the moon is 60 times farther away than we are. Newton said, what if gravity gets weaker with distance? What if it follows an inverse square law? That means if you go twice as far away, gravity becomes 4 times weaker, 3 times as far, 9 times weaker, the square of the distance. If that's true, then at the moon's distance, 60 times farther, gravity should be 60 squared times weaker. That's 3,600 times weaker. Now on Earth, things fall 16 feet in 1 second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 16 feet divided by 3,600. Do the math. 16 feet divided by 3,600. That's about 1/20th of an inch per second squared. Wait, let me say that differently. In 1 second, something at the moon's distance should fall toward Earth by 1/20th of an inch times 3,600, because we're talking about the square of time in the formula. 1/20th of an inch times 3,600 equals 16 feet, exactly what we measure on Earth. Newton calculated how far the moon should fall toward Earth in 1 second if gravity follows an inverse square law, and it matched perfectly. The moon is falling at exactly the rate Newton's law predicts. This was huge. This wasn't just a theory. This was a prediction. Newton took a completely independent fact, how fast things fall on Earth, and connected it to another completely independent fact, the period of the moon's orbit and its distance from Earth. Two things that seemed totally unrelated suddenly became connected by one law, the law of gravitation. There was no going back now. Newton went further. He calculated what the shape of planetary orbits should be if gravity follows an inverse square law. And he found that it should be an ellipse. And guess what? Planets do move in ellipses. Kepler had already measured that. But Kepler didn't know why. Newton explained it. He got 3 for 2, as it were. And then more things fell into place. The tides. Why are there tides? Because the moon pulls on the Earth. But wait, if the moon just pulls the Earth toward it, there should only be one high tide per day, right? The bulge of water on the side facing the moon.